So we have a specific form of infinite series called geometric series. And the form might be a plus a times r being a rate plus a times that rate squared plus all the way to a times r to that rate raised to a n minus 1 power. And this can be represented as the sum as n goes from 1 to infinity of a to the r raised to the n minus 1. So in this situation, a and r, they are constants. They are real numbers. One thing we know is that a cannot equal 1. R is the ratio. And the ratio is determined by taking a term and dividing it by its preceding term. So for example, R is going to equal a sub n divided by a sub n minus 1. Okay? The ratio, that can be positive or negative. All right? If r equals 1, then that geometric series would diverge. If the absolute value of r, so if the absolute value of r is less than 1, meaning we have a fractional rate, it could be positive or negative, then the geometric series is going to converge to a over 1 minus r. So what we can say then, this sum as n equals, or n goes from 1 to infinity of a times r to the n minus 1, if that ratio is a fractional value between 0 and 1 or 0 and negative 1, then it will always be equal, it converges to the value a divided by the quantity 1 minus r. Okay? And then if the absolute value of r is greater than or equal to 1, then it is divergent. And just another notation here, in this situation, the example from the book, it starts with n at 1, but you could write it differently, and you could say, well, this is the sum from n equals 0 to infinity of a times r to the n, as opposed to up above we have n minus 1. So here we have a series. It's geometric. You may not be told that from the beginning. You might have to discern that. But we want to know if it converges or diverges. And one way we can tell if a series is a geometric series would be to look at that ratio. So dividing the latter term from the prior term. So we could say 1 over 81 divided by 1 over 27. Or 1 over 27 divided by 1 over 9. And these two values need to be exactly the same. And simplifying, you get a rate of 1/3. And automatically, because we know it's a geometric series and that ratio is fractional, less than 1, we know it's going to be convergent. So the sum of this series this geometric series, which could be written as n goes from 1 to infinity of my first term, 1 over 9, times my rate, 1/3 to the n minus 1. What that would equal would be that a value, 1/9, divided by 1 minus the rate or ratio, 1/3. And in this case, the series converges to 1/6. So here we have a series, the sum from n equals 0 to infinity of -1 raised to the nth power times 5 divided by 4 to the nth. And one thing we do when we're looking at, dealing with, trying to figure out information about these series is we might write out a few of the first terms. So if I were to plug in 0 for n, I get 5. Plugging in 1 for n, I get -5/4. Plugging in 2 for n, I get +5/16. 3 for n, -5/64. And you just need a few terms to consider. One thing we want to notice, when we have a -1 raised to a power, that's indication that we are going to have an alternating series, and you'll notice these signs go plus minus, plus minus. So that's, just something to pay attention to and note. We can see what the first term here is, a equals 5. And if we want to find that common ratio, r, that would be like saying -5/4 divided by the term in front of it, 5, or 5/16 divided by the term in front of it, -5/4. And these are all going to be the same. If they're not the same, this is not a geometric series. So the last one that we could do would be -5/64 divided by 5/16. And in all these situations, it simplifies down to -1/4 to be our common ratio. And so one thing we can say here is that since that absolute value of the rate is less than 1, we know it's going to be convergent. And we have that formula for determining the value of convergence. That would be my first term, a, which is 5, divided by 1 minus my ratio, -1/4. And minus -1/4 makes that a +1/4. So simplifying this, the value that the series converges to is 4. So we're going to do another geometric series example. We're going to express this repeating decimal as a fraction. And so when we say as a fraction, we mean as a ratio of two integers. And what you notice here is we've got 5.23232323, right? And that's a repeating value. So we could write this as a sum, and that would be 5 plus those first two, that is 23, that 3 ends in the hundredths place. So the second two, we would say plus, we've got tenths, hundredths, thousandths, 10,000ths. So 23 over 10,000. And continuing along here, the next 2, 3, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. All right, so we had 2 zeros, and then we went to 4 zeros, and then we went to 6 zeros. And this would obviously continue along in this fashion. So if we think about writing it, and saying, well, that is 5 plus 23 over 100 to the first, plus 23 over 100 squared, plus 23 over 100 cubed. And you don't have to factor out a 23 over 100, but it kind of makes it a little nicer to look at, so I'm going to do that. 5, if I factor out 23 over 100 from those terms, what that leaves me with is 1 plus 1 over 100 plus 1 over 100 squared, continuing along. And so what I have in the parentheses here, this is a geometric series, right? And I could have calculated my values from the geometric series the line prior, but it's just a little simpler this way. So in this case, A, my first term is 1, and my common ratio found by dividing each term over its predecessing term, we would get 1 over 100. So the sum for this series here, S sub n, equals A, which is 1 minus 1, divided by 1 minus my R value, 1 over 100. So that's 1 divided by 0.99. So what we end up with is this is 5 plus 23 over 100 times 1 over 0.99. And I can multiply that through. I now have 5 plus 23 over 99, and adding those fractions together, I would get 518 over 99. So I've now expressed this repeating decimal as a fraction by using geometric series.